So, hello everyone. I once again welcome you all to MSP lecture series on interpretative spectroscopy. In the last couple of lectures, I was discussing about multinuclear NMR. In the beginning, I gave more emphasis for phosphorus 31 NMR, and also in between I brought other nuclei such as 14N, 15N, 19F. So, let me continue from where I had stopped. Let us look into another interesting example. So, then look into the problem shown here. Interpret the spectrum below for the compound. Methyl group is there, platinum, ethylene is there, and 2 dimethyl phenyl phosphine ligands are there. So, justify all splittings. Is this the cis or trans isomer? And the data given is 31p 100% abundance, I equals half. And of course, 195 platinum is NMR active with I equals half, and 34% abundance is there. And then 196 platinum is 66% and it is NMR inactive, I equals 0. So, with this information, and here information is not given about the spectrum shown here, which spectrum it is. So, by looking into the spectrum and also by writing all possible isomers for this compound, we should decide whether it is cis or trans. If that is the case, which NMR this spectrum represents. So, let me first write this one. So, platinum I can write P, PH, Me2, this ethylene. So, other possibility is so, these two possibilities are there, and if you consider this trans isomer, so in this case both the phosphorus environments are identical because one can perform C2 axis of rotation in this direction along with ethylene platinum CH3 axis, whereas here I do not think we can perform C2 axis C2 rotation in this direction or in this direction and to make two phosphorus moieties equivalent. So, if you consider this one, and now we have to see what nuclei NMR this figure given here the spectrum represents. Now, if we look into phosphorus now, phosphorus whether we take this one, we have two moieties, then we should have PP coupling should be there. So, then it should appear as a doublet of doublet. So, that is not there, the pattern does not look like it belongs to this kind of spectrum if it is phosphorus NMR, and if it is platinum NMR again, and this will couple with first a doublet and then doublet, again it should be a doublet of doublet, and there is a possibility of coupling with long range or 2-bond platinum to hydrogen coupling. Then that would be some sort of satellites, or if you take platinum then it should be doublet of triplets or quadrets. So, that is not there. The other option left is now 1H NMR. If we take 1H NMR, we can identify 3 different type of environments apart from phenyl region. One is methyl groups are there here, and then we have CH3 is there, and then CH2 is there. And if we exclude phenyl region, then we will come across 3 different type of environments. One is for ethylene protons, one is for methyl, and other one is for again methyl groups present on phosphorus. If we just see that one 1H NMR if we take, and this would couple, this ethylene protons will couple equally with the 2 phosphorus to give a triplet, and then each triplet will be having a satellite appears like a doublet, triplet of doublets, and that is the case in this one. For example, if it first splits into triplet, this I am writing for ethylene protons, and then because of platinum coupling we will see something like this coming here. And then here we have, so this is one set. And then if you look into CH3 proton, again CH3 also same case is there. First CH3 protons will be split by 2 identical phosphorus into a triplet, and then they are further split by platinum to showing platinum satellites here. It is also identical to what I have drawn here, and when we look into these 6 protons here and 6 protons here, they are quite similar. As a result, these 12 protons are there, so they split by again phosphorus into triplet, and then again platinum will split them into double. That means we can anticipate 3 sets of individual separate triplets in this case if it is 1H NMR, and then they will be having corresponding platinum satellites. That's what the spectrum looks like now, and you can see that expanded version here. One is at minus 1.n ppm and other one is minus 41.2 ppm and other one is 0.083 ppm. So that means without any problem we can say that this is for CH3 and this is for methyl groups on phosphorus, and this is for ethylene hydrogen atoms. So this one, and then we can say that this is 1H NMR spectrum of this trans phosphorus containing ethylene containing methyl group containing platinum compound, and then this whatever we see here, these are all platinum to hydrogen couplings. They come as satellites here. So this spectrum is for 1H NMR, and it shows for ethylene a triplet and satellites, and again methyl group a triplet because of 2 equivalent phosphorus splitting that into triplet, and again satellites, and again methyl groups satellites. Okay, so no doubt this is 1H NMR spectrum. Okay, so this is how one can analyze and interpret the data. So let's move on to other examples here. So now let's come back to lithium. Lithium, we have 2 isotopes are there. 6 lithium with I equals 1 and 7.4% abundance, and then other one is 7 lithium with I equals 3/2 and natural abundance is 92.6%. One should remember the fact that those nuclei with I greater than half are quadrupolar, and since 6 Li has lower quadrupolar moment and yields sharp signals but has low sensitivity. However, in case of 7 lithium is highly sensitive but has a higher quadrupolar moment, so its signals are always broader. And then when we look into chemical shift range, whether you consider 7 lithium NMR or 6 lithium NMR, the range is very similar for both the nuclei. You can see here lithium amide in ammonia, it comes in this range, and then external paratropic contact ions will be in this range, and aqueous lithium plus would be around 0, and solvent separated aryl ions also comes in the same range, and the external diatropic aromatic contact ions would also come here, and alkyl lithium would come around here, and sandwiched diatropic aromatic contact ions would come anywhere between -10 to 15, and also lithium plus ion in ammonia comes around -10. So now I have given here for LiCl taken in D2O with natural abundance. In case of 6 lithium it comes here. As expected, it will be a singlet. Similarly, one can also plot 7 lithium NMR for LiCl in D2O. This also is sharp singlet, you can see here. And here I equals 3/2, but it doesn't matter here, it's I equals 1 here. This would come only when we are seeing lithium is coupled to other NMR active nuclei. So now you can see here spectra are given for 6 lithium, and then these are not simple lithium compounds. The deuterium induced isotopic fingerprints in 6 lithium NMR spectra of partially deuterated organolithium aggregates. That's the reason they look not simple. Phenyllithium monomer is there here. Because of interaction of pi electrons of the carbon that is binds to lithium, they will be having a dimeric structure something like this. And of course, when you take methyl lithium or any alkyl lithium, tertiary lithium or methyl lithium, they will be having cuban type structure with this relationship would be like tetrahedral. And in this one, each methyl group, the lithium is coupled with CH3 protons to give a 1:3:3:1 triplet, and here they are coupled with methylene protons here. And of course, it is not easy to interpret it looks like it is coupled to two hydrogen atoms. As a result, it is showing a triplet because these are all partially deuterated. You never know how many CH2 are there, whether it's CHD and all those things, but from spectrum it appears that it is coupled with two equivalent hydrogen atoms. As a result, it shows 1:2:1 triplet, whereas here it is very clear methyl hydrogen atoms are coupled with lithium to show quadrate 1:3:3:1. And here one such lithium reaction is shown here. This was carried out in our group. Here what happens, the lithiation is very sensitive to temperature, and also if other acidic protons are there, you can expect the possibility of lithium exchange, although we replace with halogen exchange process. For example, this bromo compound is taken, and when it is treated with N-butyl lithium at -78°C, and then at the same temperature, if you add chlorodiphenyl phosphine after lithiation, it gives here exocyclic ortho position. Here PPH2 is added and it gives a compound like this. But on the other hand, after adding N-butyl lithium at -78°C, it initially forms this one, and in case if it is warmed to room temperature for the addition of chlorodiphenyl phosphine, what happens, the moment it is warmed above -78, that means when it starts warming up and attaining 0°C or coming to room temperature, what happens, lithium exchange takes place with this one, and then lithium will move here and H will move here, and then if we add chlorodiphenyl phosphine, so it goes to trizolic carbon. That means basically this one has to be extremely careful while doing lithium reactions. They are very, very sensitive to temperature, and if you have some acidic protons in the nearby where lithium is occupying on the carbon, there can be exchange process, and this is one such example where temperature assisted lithium hydrogen exchange takes place. Is it possible to monitor this one? Yes, it can be monitored by looking into 7-lithium NMR spectrum here. So we carried out time dependent 7-lithium NMR spectra, and a series of spectra are shown here. Immediately after the addition of N-butyl lithium, what happens, it goes through halogen exchange to orthocarbon, and with the time you can see here after 6 minutes what happens, another signal is developing towards the right side. That means lithium hydrogen exchange has started, and by the time attains 1 hour 15 minutes, complete exchange takes place, and it's no longer, lithium is no longer present on phenyl ortho position, it has moved to trizolic carbon. So this indicates sometimes this kind of variable temperature assists in understanding how this process is taking place, why I expected a phosphination at ortho position, whereas I got phosphination on trizolic carbon. So all this vital information one can extract from doing variable temperature NMR studies, not necessarily with lithium, with any other NMR active nuclei, provided it gives a clue about such reactions. Okay, so now let us look into another interesting aspect, isomerization. If you just look into this compound here, it's a multi-dentate ligand, and of course the most favored are pp chelation, but on the other hand we also have this trizolic nitrogen atoms with a pair of electrons on each one, so they can also coordinate. So here when this compound is treated with tetracarbonyl bis bipyridine tungsten compound at room temperature, initially PN coordination takes place, and keeping this in solution for 72 hours, it undergoes isomerization from PN coordination to PP coordination. On the other hand, if we take the same bisphosphine and add molybdenum here, whether it's molybdenum or tungsten, in both this isomerization happens, but only in case of tungsten it takes 72 hours, whereas in case of molybdenum within 2 minutes PN bonded compound takes place. On storing for 2 hours, within 2 hours isomerization completes and it comes to PP coordinated compound. So that means again here whether it is possible to monitor isomerization process, that means ligand being PN coordinated initially to become PP coordinated one. Yes, one can do it. I will show you here. This is for the isomerization of PN coordination to PP coordination on molybdenum, and if you take it initially, you can see two signals are there. Two signals can be seen for both uncoordinated phosphorus atoms. Since this compound here, both the phosphorus atoms are chemically and magnetically non-equivalent and they are farther from each other. As a result, you are not seeing any PP coupling, but nevertheless they show two chemical shifts that you can see here. And once after adding molybdenum complex to this one, coordination starts, and immediately you can see only one peak is there, other one is coming somewhere here, coordinated. That means basically what happens, one of the phosphorus is left uncoordinated, and whereas one of the phosphorus is coordinating. So you can see here, that means here we have a complex where we have PN coordination. Since PN coordination is there, other phosphorus and triazolic carbon is left uncoordinated, and that is here only, uncoordinated region. Little bit shift is there compared to this one. And then with the time you can see now another signal is developing here. These two are for coordinated, PP coordinated compound here. With the time it is increasing, and you can see by 2 hours within 120 minutes this isomerization completes, and then this is disappearing here. This one is uncoordinated one present on this one, this is disappearing, and after 2 hours you can see completely PP coordination, and we don't have any trace of PN coordinated compound. So that means we know now isomerization from PN to PP takes roughly 2 hours. And whereas in case of tungsten, it is taking little more time. So you can see here, to begin with, again very similar to molybdenum complex, it's uncoordinated, both are here. Within 1 hour, what happens? One of the triazolic carbon remains uncoordinated, whereas the other one is getting coordinated. As a result, what happens? The PP coordinated compound, PN coordinated compound is there, and then with the time, what happens? This is decreasing, and then it nearly takes 72 hours for the completion of isomerization from PN to PP here. And another advantage with the tungsten compound is we can see here these tungsten satellites. Tungsten is also NMR active, and we have very trace quantity here, and we are seeing the tungsten satellites, and tungsten to phosphorus 1J coupling is about, it can vary between 200 to 350 hertz. So this also we can see very nicely the satellites are coming here. So that means in case of molybdenum it took 2 hours, whereas in case of tungsten it took 72 hours, and that can be clearly seen from this time dependent 31p NMR spectra for the isomerization of complex of tungsten. So let me stop here and continue in my next lecture more interesting examples with emphasis on boron, mercury, and even including 19F NMR spectra of some of these mixed NMR nuclei compounds. Until then, have an excellent time and enjoy interpretive spectroscopy course. Thank you.